Power loss in a circuit, primarily due to heat dissipation, is a fundamental concept in electrical engineering. Understanding the correct formula for calculating this power loss is crucial for designing efficient and safe electrical systems. The most accurate formula for determining power loss due to heat is P equals I squared R, where P represents power in watts, I represents current in amps, and R represents resistance in ohms. Now, let's examine why the other options, P equals I and P equals E squared over R, are not as suitable for calculating power loss specifically due to heat. The formula P equals I, where E represents voltage in volts, calculates the total power in a circuit. While it's a valid formula for power calculation, it doesn't directly isolate the power lost as heat due to the resistance of the circuit. It gives the total power delivered, which might include power used by a load or other components, not just the power dissipated as heat. The formula P equals E squared over R is also a valid power formula, derived from Ohm's law and the power formula P equals I. However, this formula is most useful when the voltage across a specific resistance is known. While it can calculate power dissipated by a resistor, it doesn't inherently emphasize the relationship between current and resistance that directly causes heat generation. I squared R specifically focuses on the heat generated due to current flowing through a resistance. The heat generated is directly proportional to the square of the current. A small increase in current can lead to a significant increase in heat. Resistance is the opposition to current flow. The greater the resistance for a given current, the greater the heat generated. P equals I squared R directly quantifies this relationship. Here's a more detailed explanation of why P equals I squared R is particularly effective for understanding power loss due to heat. Consider a simple circuit with a resistor connected to a voltage source. Current flows through the resistor, and as it does, energy is dissipated as heat. The amount of heat generated depends on the magnitude of the current and the resistance of the resistor. If you double the current flowing through the resistor, the power dissipated as heat quadruples. This is because the power is proportional to the square of the current. The resistance acts as a multiplier, determining how much heat is generated for a given current. This formula is particularly useful in scenarios such as analyzing the heat generated in electrical conductors, evaluating the power dissipated by resistors in electronic circuits, and assessing the efficiency of power transmission lines. Let's illustrate with a numerical example. Suppose a resistor of 10 ohms has a current of 2 amps flowing through it. The power dissipated as heat can be calculated as P equals 2 squared multiplied by 10, which equals 40 watts. Now, if the current is doubled to 4 amps, the power dissipated becomes P equals 4 squared multiplied by 10, which equals 160 watts. This demonstrates the significant impact of current on heat generation. Now, let's discuss why P equals I might not be the best choice for calculating heat loss specifically. While P equals I gives the total power in the circuit, it doesn't isolate the power lost as heat in a specific resistor. It accounts for the voltage drop across the entire circuit and the total current flowing through it. Therefore, it doesn't give a clear picture of the heat generated in a particular component due to its resistance. Similarly, P equals E squared over R can be used to calculate the power dissipated by a resistor if the voltage across it is known. However, it doesn't explicitly highlight the relationship between current and resistance that is fundamental to understanding heat generation. In summary, P equals I squared R is the most appropriate formula for calculating power loss due to heat because it directly relates the current flowing through a resistance to the amount of heat generated. It emphasizes the critical role of current and resistance in heat dissipation, making it a valuable tool for analyzing and designing electrical systems. This formula is widely used in electrical engineering to ensure that components are properly sized and that heat generation is within acceptable limits. It's also essential for understanding the efficiency of electrical systems and minimizing energy waste due to heat loss. Furthermore, the I squared R formula is fundamental to understanding the limitations of conductors. All conductors have some resistance, and as current flows through them, heat is generated. If the current is too high, the conductor can overheat, potentially leading to insulation damage, fire hazards, or even conductor failure. Therefore, understanding and applying the I2R formula is crucial for selecting the appropriate conductor size for a given application and ensuring the safety and reliability of electrical installations. Understanding the nuances of each power formula, including P equals I, P equals E squared over R, and P equals I squared R, is essential for electrical professionals. While all these formulas are valid, the choice of which one to use depends on the specific application and the available information. For calculating power loss due to heat, P equals I squared R is the most direct and informative choice. This is because it directly relates the current and resistance, which are the primary factors determining heat generation. This distinction is vital in electrical design and analysis, where understanding the root causes of heat loss is essential for safety and efficiency. It's important to note that in more complex circuits with multiple resistors and other components, the I2R formula can be applied to each individual resistor to determine the heat dissipated by that specific component. The total power loss in the circuit is then the sum of the power losses in all the individual resistors. This approach allows for detailed analysis of heat distribution within the circuit, enabling engineers to optimize component placement and thermal management strategies. In conclusion, while P equals I and P equals E squared over R are valuable power formulas in electrical engineering, P equals I squared R is specifically tailored for calculating power loss due to heat. It directly links current and resistance to heat generation, making it an indispensable tool for analyzing, designing, and ensuring the safety and efficiency of electrical systems. The understanding of power loss is also critical in the National Electrical Code. Firstly, NEC Section 110.3. B requires that listed or labeled equipment shall be installed and used in accordance with any instructions included in the listing or labeling. Equipment is tested at certain ampacities and can cause a fire if not used properly. Secondly, NEC Section 110.9 states that equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment must be able to handle specific fault levels or it could be damaged. Thirdly, NEC Section 110.10 dictates that the overcurrent protective devices, the total impedance, component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices to clear fault to limit the damage. Overcurrent protection must operate properly. Fourthly, NEC Section 210.19. 8.1 states that the ampacity of the branch circuit conductors shall not be less than the maximum to be served. Branch circuits must have the correct ampacity. Fifthly, NEC Section 215.2. 8.1 says that feeder conductors shall have an ampacity not less than the non-continuous load plus 125% of the continuous load. Feeder conductors must have the correct ampacity. Sixthly, NEC Section 310.15. The 1 states that the ampacity of a conductor shall be determined by the tables or engineering calculations. The ampacity of conductors must be properly calculated. Seventhly, NEC Section 314.16 dictates how many conductors are allowed in a box. Boxes cannot be overfilled. Eighthly, NEC Section 408.55 requires that the overcurrent protection for a panel board shall not exceed the rating of the panel board. Overcurrent protection must not exceed the panel board rating. Ninthly, NEC Section 430.22 states that conductors supplying a single motor shall have an ampacity not less than 125% of the motor full load current. Conductors supplying motors must have the correct ampacity. Tenthly, NEC Table 430.52 dictates the maximum rating of a set-in of motor, branch circuit, short circuit, and ground fault protective devices. This protection must be installed properly.